Okay, so now I want to talk about the continuous functions. I mean, there are a lot of things that we can discuss about limits, but we need to move on. Okay, there are a lot of tricks about limits. Maybe we will go back to the limits if we have time. But for now, let's first go to the continuous functions. Okay, so a function f is called continuous at a point at a, which is a point. If and only if, I mean, we define it, it's the definition, define. We say the function is continuous if and only if the limit is equal to the value at this point. So this actually contains three pieces of information. So the first is that f is defined on a, right? It has to be, so when we talk about the limit, it doesn't need to have a value at a, right? But it has to have a value at every point that is close enough to a. Like it has to have values for some open interval around a, right? But for the continuous function, it has to have a value at a, so which means f has to be defined on a. So f is defined at this point a. The second thing is that it has to have a limit, right? So we want this limit exists. And the third thing is that they coincide, right? So you can see that this is not an easy thing, right? You want the limit exists, and you want the function to be defined at this point, and you want the limit coincide with the value at this point. So this is what it means. So like if it has a limit at this point, right? Then it doesn't need to have a value at this point. So let's assume that it has no value at this point. So if you want to make this function continuous, so now let's assume that the limit as x approaches a of f of x is equal to L. Then this is a and this is L. So now if you want this function to be continuous, and then you can define a value at f of a, what will be the value? Then it has to be L, right? Because if you wanted this to be true, then you have to define f of a to be L such that this is true. Okay? So, which means if you have a continuous function, or let's say if a function is continuous at this point, what does it mean? It means that for all epsilon bigger than 0, you can find some delta such that for all delta in the open interval, the entire open interval around A, including this point, then they are close enough, right? So you actually have an equivalent definition. So this is actually equivalent to that, because now you have this point, and then this the value at this point is exactly the limit, which means if you consider the difference, then it's equal to 0 when x is equal to a. Does that make sense? Because when x is equal to a, then f of x minus f of a is equal to f of a minus f of a, which is equal to 0, which is always 0, because you choose x to be a. So which means you have this equivalence. Okay, so then this is true even only for all epsilon bigger than 0. You can find some delta bigger than 0 such that for all x in R, if the distance from x to a is just less than delta, then you have the distance from f of x to not any L, but to f of a is less than epsilon. So now there are two tricks. So first, you don't have this bigger than 0 anymore, because even when x is equal to a, then this is clearly 0, right? So then even when this is equal to 0, or even when x is equal to a, this is clearly true, which means you can remove this bigger than 0 condition. And the second thing is that this cannot be any real number L. It has to be f of a, because this limit has to be f of a. And you can check that if this is true, Then on the other hand, you can prove there clearly that if this is also bigger than 0, then this is still true because this is a stronger condition than the original condition. Then this is still true. And then this will mean that for epsilon, you have some delta such that for x close enough to a, you have f of x is close enough to this value f of a, which means this is true. So this actually establishes an equivalence between these two statements, right? So this is quite symmetric. I would say this is quite symmetric because you don't have a bigger than 0. Otherwise, it's stupid. But you have to have this bigger than 0 for the definition of a limit. But in the continuous functions, you don't have this bigger than 0. And also, this L has to be f of a. So it's also like in some sense symmetric. And then you can think of this as x minus a, and then you put f on both terms, so you get f of x and f of a. So it's still symmetric, which means continuous function is quite important. And then in calculus, we are basically interested in continuous functions, and then also specifically those functions that are differentiable or differentiable functions. Okay. For now, we are only interested in the continuous functions. Okay. So this is about continuous functions. So we have seen one example, which is all polynomials are continuous. So we can actually use the limit law to prove something similar. So like the sum of continuous functions is continuous, the difference of continuous function is continuous, the product and then the quotient of continuous functions is continuous if the quotient is not if the denominator is not 0. So which means you can actually show that the sum or difference, or actually scalar multiple, it doesn't matter, scalar multiple, or let's say the product, or the quotient of continuous functions. I would just write CONTI for continuous functions. Okay, CONTI. So continuous functions is continuous. Okay, so how do we prove it? I mean, for the quotient, then you want the denominator to be non-zero. Okay, for at least a small interval around that point, rigorously speaking. But you can just assume the quotient is never 0. Then it's clearly true. So let's prove it. So maybe we'll just prove one of them. So let's prove the sum of continuous function is continuous. I mean, it's actually a simple corollary from the limit laws. Okay, it's not hard at all. So now let's prove. So let's do an exercise. We want to prove that if f and g are continuous at a, then f plus g is continuous at a. Okay, so first, what does this mean? Okay, so proof. So we have two conditions. So now we have the limit as x approaches a of f of x is equal to f of a. And then the limit as x approaches a of g of x is also g of a. So then by limit law, since both limits exist, then we can use the sum rule to deduce that the limit of the sum exists. And then it will be equal to the sum of these two limits. And then by assumption, because they are continuous, so we can evaluate the limit just by looking at the value at this point, which is f of a plus g of a. And then, so this means if we look at the function of f plus g, so this is the function, this is the summation, right? This is f plus g evaluated at x. And this is f plus g evaluated at a, right? So then you can see that the limit of this sum function will be equal to the value at this point for any, at least for this a. So this means it is continuous at this a, okay? And we actually define continuous functions pointwise. which means we define a function to be continuous on a set if and only if it's continuous at all the points. Okay, so usually we define that f is continuous on a set A in R if and only if for all A in A, f is continuous. But sometimes we have a different definition. But now at A, let's just use this notation. So just by exactly the same argument, I mean the main part of this proof is just this limit law. So you can prove similarly that you can prove all the other are correct just by applying the limit laws, and you win. Okay, and you have some special functions that we want to discuss. So the first one is x to the power of some alpha. So here we must be very careful about this alpha. So maybe we just look at x to the some examples. Okay, so what is x to the 1? It is this function, right? So it is continuous everywhere. And what is x squared? It is something like this. Okay, this is x squared. What is x cubed? It is something like this. Okay, and what is x to the 4th? Then it's something like this. X to the 6, x to the 5, it's something like this. And then you get x to the order, like let's say the positive powers. Okay, or I mean, or the integer or the positive integer powers. And we can also define, for example, x to the m over n, but let's just forget about for now. And let's look at x to the power of 1/2. So then this is going to be square root of x, and this is only defined for x bigger than or equal to 0, which means the domain is the half open half closed interval from 0 to infinity. But when you look at x to the 1/3, which is the cube root, then you can define values like this, x to the 1/3. You can define the cube root of negative numbers. So the domain again becomes the entire real numbers. So this is cube root of x. And you can define the 4th root of x, and then the 5th root of x like this. Okay? Okay. And then you can see that all these functions are continuous. Well, not prove, but you just take it for granted. They are all continuous in on their domain. And then for this kind of function, when we say it's continuous, we are looking at the so-called the right limit at this point. So which means we only care about x that are only in the right half of the interval. Okay, so we will not talk about the definition of one-sided limit for now. We just take it for granted. Okay, you just look at this graph and then take it for granted. And okay, so we can now, I mean, we look at all the a to the power of x, where a is some number that is bigger than 0 and not equal to 1. So there are two cases. So if a is bigger than 0, it's something like this. So for example, e to the x, or let's say 2 to the x, or 1.1 to the x, just any a to the x where a is bigger than 1. Then you get something like this. It's kind of an exponential function, okay? Then the thing is that it has to pass the point 0.1. And it's clearly defined everywhere on the real numbers, but the values has to be bigger than 0. So the values must be bigger than 0, but it's defined, the domain is R, right? It's defined for all real numbers. And if a is from 0 to 1, so for example, if a is 1/2, so 1 over 2 to the power of x, or 1 over 2 to the x, or let's say 0.1 to the power of x. So whenever you have some number that is between 0 and 1, then the graph would be something like this. It will be decreasing. I mean, this is increasing, right? And then this will be decreasing. So this is the graph of a to the power of x, where a is from 0 to 1. So here, still, if you look at the values, they are always positive. And it's also defined on R, but you can see it's kind of it's very different when a is bigger than 1 or less than 1. I mean, given that a is positive. So you have to keep that in mind. But they're always continuous. You just take it for granted. It's always continuous. So for example, if you look at the limit as x approaches any point, let's say pi, and then a to the power of x, then this is a to the pi because it is continuous. Okay, just take it for granted for now. You can prove them rigorously, but you then will be, you have to be careful about the definition of exponential function. If you want to really do everything rigorously, it will take a lot of time, but you can do it in the end. You can do it, but you have to be very careful how to define an exponential function or like a power function like that. And also we have to define the log, okay? The logarithmic function. So there are also two cases. So for this one, it's log ax. So it must pass the point a comma 0. Oh, sorry, 1 comma 0. So this is when a is bigger than 1. Okay, then it'll be increasing. It's also continuous, but it's only defined, or the domain is only 0 to infinity. Okay, it's the open interval. And then if you look at log, so for example, this is the graph of ln of x, which is the log e of x. And also this is the graph of lg of x, which is log 10 of x. Okay? And this is also the graph of log 2 of x, for example. So, but this is not the graph of log 1/2 of x. Okay, it's not the graph of log 0.1 of x. So the graph of log a of x, where a is between 0 and 1, then it's something like this. It must pass the point 0, 1, and it is decreasing. And the domain is also all the positive numbers, so from 0 to infinity, the open interval from 0 to infinity. And the log functions are also continuous on their domain. Okay? And by the way, for the function, I think I have totally forgot to just emphasize, like, this is 1 over x, okay? And similarly, this is 1 over x cubed. But then for 1 over x to the even power, then this is 1 over x squared. This is 1 over x squared. And then this is 1 over x to the power 4, 1 over x fourths. So they are not continuous at this point because it's kind of like broken at this point. But it's continuous here and it's continuous here. So it's continuous on the open interval of the union of the open interval from negative infinity to 0, union the open interval from 0 to infinity. So for these two functions, it's continuous on their domain, which is from negative infinity to 0, union 0 to plus infinity. And then, here actually every graph is continuous on their domain. So for example, here you can also evaluate log a of x when x approaches pi. Then this is going to be just log a of pi. Okay, just plug in the value. It's what it means for continuous functions. And then we can look at the trigonometric functions. And then maybe also we'll talk about the inverse trigonometric functions later. But let's just first talk about the trigonometric functions. So, all I want to emphasize is that, so this is sine, okay? And then this is cos. And then this is tangent. Maybe I need to have a new page. And then this is tangent. Yeah, okay. And then all the other points. So the importance of the trigonometric functions is that you will use it later, and I cannot talk about any applications until you have seen some more advanced maths. But just for now, let's just look at the trig functions. So at least all of them are periodic, okay? So at least they are periodic of period 2 pi. But for example, the tangent function is periodic of period pi, okay? So for the sine functions, for the sine function, it is 0, and then when it goes to pi over 2, it becomes 1. And when it's equal to pi, it becomes 0. When it's 3 pi over 2, it becomes -1. And when it's 2 pi, it go back to 0. And when it's, so you can continue this step. So then this is called a period. But also you can think of this as a period, right? And also you can think of this as a period. You can think of this as a period. You can even think about this as a period. So as long as the length is 2 pi, it is a period, okay? So it is periodic of period 2 pi. And also it is actually symmetric along this line. It's symmetric along x equals 2 pi. Because if you reflect the graph along this axis, if you reflect anything from the left to the right, then get exactly the same thing. So this means the graph or sine is symmetric along x equals pi over 2, but also it's symmetric along 3 pi over 2 and then anything like that. So it's actually symmetric along all the x equals pi over 2 plus some integer k multiplied by pi. Okay, so here k is some integer. We denote it by k in z. Okay, so this is pi over 2. This is we add half period. We add a half period, which is pi. Yeah, it makes sense because from here to here, it's not an entire period. It's half period, which is pi. Okay, so which means we can go from left to right by plus pi, but we can also subtract by pi. So then we get pi over 2 plus k pi. Okay, and it's symmetric along all these lines, and it will be important later. So for the cos function, it's actually basically we just translate the sine functions to the left by pi over 2. Okay, or you can just describe it. I mean, it's almost the same. It's still periodic of period 2 pi, and then it's symmetric along all the lines that are simply just k pi or 0 plus k pi. It's symmetric along x equals 0, x equals pi, x equals 2 pi, etc. So so here the value I want to emphasize one more time. So the value at 0 is 1 when it's, I mean, this is the cos function, this is sine. So when it's pi over 2, it becomes 0. When it is pi, it becomes the lowest point, which is -1. And when it is 3 pi over 2, it becomes 0 again. And when it is 2 pi, it becomes 1. Okay? And it's periodic of period 2 pi, and then this is an entire period. So you can continue this to the right or to the left. Okay? So this is for cos. Maybe we can call it cos x. Okay, y equals sine of x, y equals cos of x. And then we can also define y equals tangent of x. So this is periodic of period pi. And then this is the entire period. This is also entire period. So this is from negative pi over 2 to pi over 2. And then, so this must be 3 pi over 2, okay? And if you look at the point when it attains the value 0, then it is 0 here. And then this, because the period is pi, so this is pi. So this is minus pi, and etc. So this will go from negative infinity to plus infinity. Okay? So this is the tangent function. And then you can just define or you can just look at 1 over tangent to define cotangent point-wise. Okay, so then you can define the cotangent, and then you can define the secant as 1 over cos of x. You can define cosecant as 1 over sine of x. So then you can just look at all the graphs of the trigonometric functions. I mean, all 6 of them. And then later we will talk about the inverse trigonometric functions, which means we focus on some subinterval of the domain, and then we define the inverse of the function on that subinterval that we particularly choose. Okay, so we'll talk about this later. So the point is that still for this tangent function, or like for sine or cos, they're still continuous. So which means everything is continuous on their domain. So here, for example, for the tangent function, I mean for sine and the cos, it's clearly defined on every real number. So the domain are both the set of all real numbers. But then for the tangent function, it's not defined for all the pi over 2 plus some integers times pi, where pi is a period. So the domain will be just r, and then minus the all the set of all pi over 2 plus some k pi, where k is an integer, right? So this is about trigonometric functions. And then later, maybe you will see some hyperbolic functions, and then even inverse hyperbolic functions. But for now, still, let's forget about it. Okay? I mean, all we need to know is that everything is continuous, but you have to prove. And then, in terms of proving it is continuous, the more trickiest, the trickier thing is how you will define these functions rigorously at every real number. So you have to know what is a real number. So you can define a real number either by Dedekind cuts or Cauchy sequence, and both of them, or any other methods. I mean, there are, I think, at least 7 different ways that are equivalent that you can define real numbers, but none of them is trivial. Okay, everyone is non-trivial in some sense. So because we have different definitions. I mean, every one of them is not easy to understand of the real numbers. So it's not easy to really define all these functions. So we have to take it for granted for now. And maybe later, if some of you are interested, you can learn more. But for now, we take a lot of things as granted. Okay? So I think it's I've discussed a lot about the continuity. So maybe in the next video, I will first talk about the limit at infinity, or when the limit is equal to infinity, or when both of them is true. So like when the limit at infinity is infinity. And I will also tell you something about discontinuity, like what it means for a function to be not continuous. And also I will define like one-sided limits of a function. Okay, so I will see you